Hello and welcome back to Nunley Math. I am your host, Aaron Nunley. I want to thank you so much for joining me here today as we continue our look at systems of linear equations and how we can use those to solve application problems. We are now several videos into that series, and we've looked at, first of all, some generic systems problems, and then we talked about some problems that are traditionally very challenging for students. We talked about digit problems, we talked about coin problems, and we talked about distance problems. Now today we're going to take the idea of distance problems a little further, and we're going to look at some problems that some people consider to be quite challenging. In fact, you'll notice that I've referred to this as the infamous train problem. Train problems are one of those problems that students over a long period of time have just consistently had a difficult time with. In fact, the train problem has become so infamous that the cartoonist Gary Larson, in his strip The Far Side, actually created a math-phobics nightmare comic based on the idea of a train problem. So hopefully, as we're working our way through these, you'll find that they're not as difficult as you may have thought. As always, the key to working through something like this is to go slowly, take your time, pay attention, organize your thoughts, draw diagrams. All those little things that we tend to rush through and overlook really make a huge difference in terms of our ability to understand the problem. So, this is an example of a classic train problem. If a train is traveling at 32 miles per hour and a car is traveling at 55 miles per hour, how long will it be until the car catches up with the train if the train left 4 hours before the car did? Now, as always, we are going to begin with identifying our unknown or our variable and then walking through a diagram of what that problem might look like. So when I read this, I look at the question. The question says, how long will it be until the car catches the train if the train left 4 hours before the car? Notice we are looking for the car's time. The car's time. It's important for us to identify that because the time the car travels is different from the time the train travels. The train actually left 4 hours before the car did. So we're going to be dealing with two different times. I list both of those even though the problem only asks me for the time the car travels because I'm pretty sure I'm going to need that train time anyway. So I'm going to go ahead and put it down. So I show my car going on a drive. I show my train going on a drive. Some people ask me why I listed the car first and the train second instead of the other way around. It really doesn't matter. I put the car first because I was most concerned with the time the car travels, and so I wanted to begin there. As always, our distance equals our rate times our time. Notice I used D1, R1, and T1 because this is just a generic formula, and the train's distance, rate, and time could be different. Do we know the car's distance? Well, that's not given to us anywhere, so I'm going to keep that. We need the equal sign. Do we know the car's rate of speed? Well, yeah, that's given to us right here. It's 55 miles an hour. Do we know how long the car travels that speed? Well, no, that's what we're asked to find out. So we keep that as well. Let's talk about the train. The train has a distance 2, a rate 2, and a time 2 because we're not certain when we begin the problem if they are the same or not. Our distance 2 is not given, but it is equal to rate 2, which is given. The train's rate of speed is 32 miles an hour. And we don't know the train's time either. Notice we indicated up here that the train's time was T2. Now, some people say to me in my class, couldn't we take that T2 and replace it with something based on this equation? Absolutely. We know that T2, or the time the train travels, is, let's see, the train left 4 hours earlier than the car did, or 4 hours before the car did. So if the car has traveled 1 hour, the train has traveled 4 more than that. It's been on the road for 5. It was on the road 4 before the car started, plus 1 extra. If the car has gone 3 hours, well, we know the train went 4 hours before that, plus 3 more to make 7. Because of that, we can actually take this T2, this train 2 time, and replace it with the car's time plus 4. Now, I kind of took a little shortcut there. Technically, what I could have done is come over here and written T1 equals T2 plus, or T2 equals T1 plus 4, and then gone back and substituted later, but my students said they preferred it if we went ahead and did it right now. We said when two objects are moving the same direction, the distance between them is always the difference between their two individual distances. What that means is that the distance between the car and the train is however far one of them has gone, take away however far the other one has gone. If the car has gone 10 miles and the train has gone 15 miles, then because they're going the same way, there would be 15 minus 10 miles between them, or 5 miles between them. We talked about this quite a bit in the last video. If that's uncomfortable for you, you may want to go back and watch that. Let's talk about what we can do next. We have a D1 formula. That's the car's distance, rate, time. We have a D2 formula. That is the train's distance, rate, and time. And now we have a formula that allows us to compare D1 and D2. We can now go through and begin filling in pieces of information we know, and then substituting in for D1 and D2. Let's look at this again. Do we know the distance apart? I can tell you that in this case, we're trying to find when the car catches up to the train. If the car catches up to the train, then the car is 0 miles behind the train. Notice I went ahead and took my D1 and I used this formula at the top and replaced it with 55t. That's substitution. I took my D2 and replaced it with this equation right here because those are equivalent. That's substitution. Notice now you have an equation in one variable that we can solve. I am going to go ahead, since these are both T1, and I'm going to start writing that both sides. And then I can divide by 23 on both sides to find the time that the car travels. If I wanted to find the train's time, I could do that, but I'm not asked to do that, so I won't. The car will catch up to the train in about 5 hours and 44 minutes. I went ahead and took that 17/23 and changed it into minutes. There again, once we get things organized, the solving is not too bad. Once again, some of you may remember this step right here from something we did in the first quarter. It says the distance apart equals rate times time minus rate times time. You could actually begin this process here depending on your comfort level with this pattern. What I'm showing you up here is where that pattern comes from. At 7 a.m., two trains leave different cities heading toward each other at different speeds. Train A, traveling 70 miles per hour, leaves Westford headed toward Eastford, 812.5 miles away. At the same time, Train B, traveling 60 miles per hour, leaves Eastford heading toward Westford. When do the trains meet, and how far from each city do they meet? Notice there are two questions here. When do they meet, and how far from each city do they meet? Knowing those two pieces of information, we can probably assume that we're going to have to find the answer to the first question before we find the answer to the second. So Let's set up t for our time. Notice I just used t because both trains are leaving at 7 a.m. and they're going to continue headed towards each other until they meet. Since they both start and end at the same time, we can just use t. Let's draw a picture of that. Train A goes 70 miles an hour headed east. Train B goes 60 miles an hour headed west. And the total distance apart is 812.5 miles. Each of these is going to get a distance equals rate times time equation. The first train, we don't have a distance. We do know the rate of speed is 70, but we don't know how long it's going to take. Notice I did go ahead and use a t because the two trains will have the same amount of time. The second equation, I still don't know a distance. I also know the rate, and I still don't know the time, but I do know that the time is the same as it was over here in the other with the other train. So they're both moving the exact same amount of time. And I also know that to find the total distance they must travel, the total distance is the sum of the two distances. I know that because they're headed in opposite directions. So if they're going to cross 812.5 miles, whatever train A does, combined with whatever train B does, we'll have to add to that amount. We talked about this at length in the last video. If you're unsure, make sure you go back and check that out. I now have three equations. Let's start filling things in. We know the total distance is going to be 812.5 miles. That's given to us. We know that D1 is equivalent to 70t using substitution. We know that D2 is equal to 60t using substitution. Now we have a single variable equation. Combine our like terms, divide both sides by 130, and it comes out as 6.25. That tells us that they will meet in 6.25 hours. Notice the question says they left at 7 a.m. and when do the trains meet? We probably need to go ahead and put this as a time. 6.25 hours after 7 a.m. is, what is that? That's 13.25. Noon is 12, so this is going to be at 1:15. That's 6 hours later and a quarter of an hour later. This is 1:15 p.m. or in the afternoon. Let's keep going with this. The second part then says, how far from each city do they meet? Any idea how we could do that? Well, notice that we do have distance formulas. Distance equals rate times time. This is the distance formula for train A. I still don't know the distance. I now know the rate of speed, and I now know the time. The same is true over here for train 2. I still don't know the distance, but I do know the rate of speed, and I do know the time. If train A goes 60 miles an hour for 6.25 hours, and train B goes 60 miles an hour for 6.25 hours, then train A will go 437.5 miles, and train B will go 375 miles. Writing that up in a sentence, the train that was headed east will be 437.5 miles east of Westford and 375 miles west of Eastford. Here again, it's all about organization, getting your thoughts together and remembering this distance formula. Let's step into something that's slightly different, but it is very much related to this. We call it the plane problem. An airplane flew for 5 hours with a tailwind of 25 kilometers per hour. The return flight against the same wind took 6 hours. Find the speed of the airplane. Notice there's a word in here we don't necessarily know. We call it tailwind. Tailwind. If you don't know the definition of tailwind, this becomes a very, very difficult problem to solve. So let's talk about tailwind for just a second. If I have an airplane, and that airplane is traveling 100 miles per hour, but the wind starts blowing from behind, That's considered to be a tailwind because it's aimed at the tail of the plane, or it's coming from the tail of the plane. If this wind is blowing at 20 miles an hour, it's helping to push the plane forward faster than it would have normally gone. So instead of moving 100 miles an hour, the plane is actually moving 120 miles per hour relative to the ground. Looking at that a different way, if I have a plane that's moving 100 miles per hour and it's in a box of air, but the air itself is moving 20 miles per hour, then I'm traveling a total of 120 miles per hour. That's a tailwind, The actual speed of the plane is what the plane can produce on its own, combined with whatever extra help it's getting from the wind. Or here's another way. You can think of this as a treadmill, or the treadmill effect. Have you ever been to the airport and seen those moving sidewalks where people come and they climb on the sidewalk, and the sidewalk helps to propel them along at a greater rate of speed than walking alone? That's the same principle. If somebody can walk 2 miles per hour, but the treadmill itself or the floor itself is also going 3 miles per hour, then the person is actually moving 5 miles per hour. Their actual speed is how fast they can walk combined with how fast the treadmill goes. Consider this. If I'm running on a treadmill at home, and I'm running 10 miles per hour, but the treadmill is set at 10 miles per hour. If the treadmill is moving in the opposite direction that I am, then my running and the treadmill are undoing or counteracting the work of one another. In other words, if the treadmill is spinning backwards at 10 miles an hour, and I run forwards at 10 miles an hour, I actually end up staying stationary or moving 0 miles per hour. This is kind of how headwind works. How headwind works is it says if I have a plane that's going 100 miles an hour and the wind is blowing towards the front or the head or the nose of the plane at 20 miles per hour, then the wind is slowing the plane down. My actual speed is only 80 miles per hour. Or another way to think of that is this. If I'm moving through the air at 100 miles per hour, but that box of air, the air itself, is moving backwards 20 miles per hour, then I'm only moving 80 miles per hour. That's how headwind works. Now that's going to help us as we're working our way through this plane problem, because the actual speed of the plane in a headwind is the plane's speed minus the wind's speed. So what does that look like? Well, let's see. The problem is find the speed of the airplane in still air. So I assign that a variable. Notice I'm using r for plane speed because I don't expect the plane speed to change. There's not 2 planes like there were 2 trains, but there are 2 trips. There's my trip into or with the wind, with a tailwind, where the wind is blowing at my back, pushing me one direction. And then I turn around and head back home, so now that same wind that was blowing from behind my plane, pushing me along faster, is now slowing me down. And just like before, I'm going to start with my distance, rate, time equation. But what we have to understand in this problem is that my rate of speed is not what's given to me in the problem. According to the problem, I don't know my rate of speed, but in both cases, the wind is altering that speed by 25 kilometers per hour. You see, my speed here is my plane speed. Let's see if I can write with this thing. Is my plane speed affected by the wind? Now, whether the wind is helping or hurting depends on which direction I'm going. It could increase my speed or it could decrease my speed. Let's talk about the tailwind. In a tailwind, The wind is blowing from behind the plane and it's helping me to go faster. So whatever the rate of speed for my plane is, the wind is going to increase that. So my rate of speed for R1 is actually the sum of the plane and the wind. And I still have my time. If I'm in a headwind, the wind is blowing from the front of my plane, slowing me down, so it's my speed take away the wind. So if I'm going 100 miles an hour and the wind is 20 miles an hour, I'm actually only moving 80. Let's go through this and fill in the things we know. Do we know the distance we travel? That's not given. Do I know how fast the plane goes? Well, that's what I'm asked to find out. Do I know how fast the wind is? Well, yeah, the wind is 25 in both problems. Do I know my time? Well, the time is different in each direction. So let's do the tailwind. My distance is going to be equal to however fast my plane can go plus the extra 25 miles an hour from the wind. And because of that, it's going to take me 5 miles to reach whatever, or 5 hours to reach whatever my destination is. On the return trip, the wind that was helping me is now slowing me down. So my actual speed is the rate of the wind, or the rate of the plane, minus the 25 miles an hour for the wind. Because I'm now going slower, the trip I was able to complete in 5 hours now takes me 6 hours. If you've done much flying, you know that when you fly east to west in the United States instead of west to east in the United States, the same distance actually takes you longer. The reason for that is because the wind or the jet stream is actually speeding you up one direction and slowing you down the other. One thing I want you to notice real quick is this. We have 2 equations in this system. We have 2 variables in this system. We don't actually know the distance we're traveling, but that's okay because we can use the substitution method to set up the equation. Notice if my distances are equal to each other, which they should be if I make a trip and I make a return, then I can take one of those distances and replace it with the first equation. I can take the other of those distances and replace it with the second equation. Notice I now have a single variable r, property of equality, your speed is 275 miles per hour. Notice, once you know how fast your plane is going, 275 miles per hour in still air, all you have to do to find the distance is pick either of these equations and plug that speed in. It's 1,500 miles each way. If you were to plug it into the other equation, it actually would come out exactly the same. So it's kind of neat that way. One last example. This is a boat problem. It says a boat takes 5 hours to travel 60 kilometers up a river against the current. The return trip takes 3 hours. Find the speed of the boat in still water and the speed of the current. Notice that we have a boat traveling with the current. If I have a boat traveling with the current and the boat goes 5 miles an hour and the current goes 2 miles an hour, then my boat is actually traveling 7 miles per hour. When my boat travels against the current, if the boat is going 5 miles an hour and the current is going 2 miles an hour and you subtract, it ends up being 3 miles per hour. Notice, just like the wind, the current either helps or hurts depending on which direction I'm going. That's why when you go canoeing, it's always harder to paddle upstream than it is to paddle downstream because the current is not helping you, it is hurting you. It's also why if you rent a canoe, most of the time the canoe livery will start at the top of the river, let you float down the river, and they'll give you a ride in the car on the way back. Notice it says find the speed of the boat in still water. Notice that mine still says still air. That's because I did cutting and pasting. So we'll just change that to water real quick. If I'm going against the current, what that means is the water is going to be hurting me. If I travel with the current, it means the water will be helping me. So when I set up my distance equals rate times time, just like with the wind, I have to take the current into account. My speed is not just the boat speed, but it's the boat take away whatever the current is doing, or the boat plus what the current is doing. It depends on if the current is helping or hurting. Against the current or upstream slows me down, with the current or downstream speeds me up. Can you fill in the values you know here? Here's what I have. I know it's 60 kilometers up the river. I don't know my boat speed, I don't know the current speed, but I know the whole trip takes 5 hours. How about the second one? Can you do that on your own? Here's what I have. 60 equals R plus C. Here the current is making me go faster, so the trip takes less time. Notice, once again, I have my two equations, so I have my system. This one's interesting because in most of them the D is unknown, but in this problem we actually have the D. So we can solve this system just as it is. I'm going to do something really cool here. Ordinarily I would have you distribute the 5 and distribute the C. I'm actually not going to do that this time. Let me erase that. I'm not going to do that this time because if I were to distribute the 5 and distribute the C, I would have these equations in standard form, and then I would just use linear combination. Instead, I'm going to do something really cool. I'm going to use my property of equality, and I'm going to divide both sides of this first equation by 5. If I had used my distributive property, this would have been 5r minus 5c, which would have been divided by 5 and would have left you with just r and c. But rather than distributing then dividing it away, I figured it would be easier or faster to divide it away at the beginning. Notice, of course, 60 divided by 5 is 12. Down here, I'm going to do the same thing. I'm going to divide both sides by the 3. Notice that 3 divided by 3 becomes a 1. 60 divided by 3 is a 20. And I get 20 equals r plus c. Again, I could have used the distributive property and then linear combination that way, but it seemed to me if I could get rid of the 5 and the 3, then I could use linear combination or the elimination or addition method with those two equations. Notice that 12 plus 20 is 32, r plus r is 2r, negative c plus c is no c's, and I'm left with this really short equation. Divide both sides by 2. The rate of my boat is 16 kilometers per hour if the current is not helping. Now, I was asked to find the rate of the boat and the rate of the current. Once you know one, we know that all we have to do is plug that value in and solve to find the other. The current flows at 4 kilometers per hour. Notice, when I'm traveling with the current, my boat is going 16 plus 4, or 20 kilometers per hour for 3 hours, which is 60. When I'm going against the current, I'm actually going 16 minus 4, so I'm only moving 12 miles an hour for 5 hours, which is also 60. Now I know that was probably pretty intense. That's some pretty complicated mathematics right there. But hopefully, as you've watched, you've caught on to this idea that the pictures can help organize things, and understanding what a current and a wind will do to your problem certainly is going to be beneficial as well. If this was difficult for you, I do suggest trying to watch it a couple times as you're working through some problems on your own. It does get easier as you see them over and over again. Just know that when I did this, I actually had to pause and cut and edit this a few times just because it is so complicated to get the explanation out in a way that makes sense. So I do understand that this is a difficult thing to do. As always, make sure you hit that like button. Make sure you leave me a comment in the comment section. Make sure you subscribe and turn on your notifications so you don't miss any other curriculum coming out of Nunley Math. Thank you so much for your attention. Best wishes to all you guys. Take care.